Right. Good afternoon, colleagues, students, friends. And today, I have the great pleasure and honor to have Professor Hiroshi Isozaki to give this HKIAS visiting lecture. And actually, Professor Isozaki is visiting us as a HKIAS visiting fellow. And we'll stay here for 2 months. And discuss with colleagues and students if you're interested about this research here. So now, next, let me give a very brief introduction of Professor Isozaki. And Professor Hiroshi Isozaki graduated from Kyoto University, Japan. And he worked in Kyoto, Osaka, Tokyo Metropolitan, Tsukuba universities. And now is a professor emeritus of Tsukuba University. And also a special invited professor of Lincoln University. And his main research field on mathematical physics, especially on the spectral theory and the scattering theory. Now, actually, Professor Isozaki is well known for his very hard analysis on the scattering theory, the spectral theory. And we have been interacting with each other for a long time, because I'm also working on this scattering and inverse theory. And I think we know each other a long time, maybe more than 10 years. Okay. Yeah. I definitely admire his, a lot of, hard analysis techniques, especially wrote several, at least 2 years long books on scattering and spectral theory, which benefits a lot for my research. And today, Professor Isozaki is going to talk about this inverse scattering, a non-compact Riemann manifold in general matrix. The next topic is.
Thank you very much. Thank you very much. Of course, I'd like to thank Professor Liu for making an opportunity in this university. It's a great honor for me to give a talk here in this institute, the best institute I've ever visited. As the title shows, my topic today is related to physics. So let us start with an elementary physical background. Now, what is inverse scattering? So let us recall the famous experiment of Rutherford in atomic physics. He prepared a material, a foiled core, and hit it by a beam of particles. Then, almost all particles go through, however, sometimes some particles are reflected with a big angle. He computed using classical mechanics and concluded that the atom occupied a very small region of the space. So what he did is, from the scattering data, he considers the structure of the type. This is the typical scattering theory. Let us also recall another mathematical paper written by Ambarzumian in 1924. He was an astronomer, not a mathematician, but of course he's very strong in physics, but he was an astronomer. And he wanted to know the structure of the nebula. So nebula is of course, it's a very, very big subject, very big object. However, because it is remote, very far from here, it's almost 1 point. And then he wanted to know the size or the shape of this nebula by the observation from the side direction. So what he did is actually to study the inverse problem of the differential equation in a bounded set of the space. So this is Another big important theme of the talk today, inverse scattering and also inverse boundary. Now, first we will pick up the shredding operation as an example and introduce an important terminology, Heisenberg S matrix. Now, you prepare some material and you heat it by a particle. In the remote path, when time is almost minus infinity, the particle moves almost free, as if there were nothing. So the wave function for this particle is a solution to this free shredding equation, where this delta is Laplacian in the standard Euclidean space. Then it approaches to the scattering center. Then it is now this wave function is governed by this Schrödinger equation with a potential term. So for the wave function, first satisfies this equation and then satisfies this equation. And in the remote future, the particle moves far away from the scattering center, and then it behaves like a free particle. So this U0, now this U0 plus T solves the free Schrödinger equation. But let us recall that this free solution is written by some data near minus infinity, time minus infinity. And this data, F plus is the data at infinity. So the mapping from F minus to F plus, it means that it's the mapping from the data of remote past, the data remote future, is the scattering of it. And this functions, F plus and F minus, have special properties. You take the Fourier transform. I will explain later. Anyhow, let's take the Fourier transform. And restrict it over the sphere of radius square root lambda. Lambda corresponds to the energy of the beam of particle. Then there is an operator on the sphere, such that if you multiply this S operator to this variable, this function on the sphere, then F minus becomes F plus. So this operator on the sphere is called Heisenberg's S matrix. So this Heisenberg's S matrix maps the data from time minus infinity to the data at time infinity. It means that it is related only to the particles very far away from the scattering center. So they are considered only on the infinite amount of the space. Now, so let us recall some terminologies. Usually we call such an operator a Schrödinger operator. And where V is a real value function, and for example, today I consider it to be a smooth function of compact form. And when there is no potential, we write H0 instead of H. The spectrum means that energy level which the particle can take. So for the Fourier operation, the energy is in between 0 and infinity. And this is also the case when we have a potential. So the Schrödinger operator with potential have 0 infinity as a spectrum. However, it also has spectrum below 0. They correspond to the energy level. in which the particles moves near the atom, near the center, near the nucleus. So the spectrum of the Schrödinger plane consists of two parts: this discrete spectrum and this zero infinity part, which we call essential spectrum or the continuous spectrum. Now, how do we compute this spectrum? We do like this. Consider this trigonometric function. This is a standard plane. It satisfies this equation. This is an eigenvalue equation or a Schrödinger equation. And consider this transform by using this trigonometric function. This is called the Fourier. This is a Fourier. Fourier called the Fourier image function. Then you can show that every function on L2 on Rn can be expanded by this plane waves. This is Fourier's inversion form. And surprisingly, this is also the case for a Schrödinger plane with a potential. Instead of this plane wave, you have a solution to this Schrödinger equation with potential, such that if you consider the integral transform like this, with phi instead of phi there, then any function on Rn can be expanded by this function of phi xc and some term coming from the discrete spectrum of the Schrödinger plane. So in this way, there is a complete system of eigenfunctions by which we can extend all functions on Rn. And so this phi of xc is called the generalized eigenfunction of the Schrödinger operator H. Now, let's go to physics a little more. Now, so first we consider an incident wave, which is almost perfect in the past. And it is affected by the target, scattering target. Then this solution, generalized eigenfunction, has this type of asymptotic expansion. The first term is like a plane wave. So it oscillates like a plane wave. Near the target behaves like a spherical. So it is expanded like this. The first term is the plane wave, and the next term has this spherical wave. And so this is the incident wave with having the direction omega, and this is the scattered wave reflected to the direction c. And there is an amplitude term. This term is important because if you consider the square of the modulus of this A, this is proportional to the number of particles reflected the theta direction over the number of all particles. So this A can be computed from physical experience. And if you consider the integral operator with this kernel A, which is the scattering amplitude, and by multiple some constant depending on lambda, the operator S lambda defined by identity plus A lambda is just Heisenberg's S matrix. So in this way, S matrix is directly related to the experiment because this is a term coming from the experiment. And And we are observing only the data at infinity. However, it is believed that S matrix is equivalent to the original physical system. So it means that physical system is determined by only the knowledge of the scattering particles at infinity. So the inverse problem is formulated as follows. Can we compute the potential wave from this scattering wave? So I use the general function, eigenfunction, to formulate this inverse problem. However, we have an equivalent formulation, which is a little shorter than the one I explained. Consider this incoming spherical wave. Spherical means you have some term which goes to zero uniform way, and then a phase factor minus here. You have minus sign here. We call it the incoming wave, incoming spherical wave. Then, given any incoming spherical wave, you can find unique solution, the Schrödinger equation, and also outgoing spherical wave. It means that now the sign is plus. Then, for any incoming wave, you can find a solution to the Schrödinger equation, the outgoing spherical wave, such that U is expanded like this as R tends to infinity. So the solution of the Schrödinger equation can be written as a sum of outgoing wave and the incoming wave near infinity. And the operator mapping A in to A out is the S matrix. It is there is a small difference, but it is equivalent with the scattering matrix I defined before. And this formulation can also be used to the wave equation. You consider this wave equation with coefficient Gij here. So this describes a wave of medium, and we consider the time periodic solution to this equation. Namely, we consider solution of this equation, which is written as a product of a time factor and the space factor. And this wave satisfies this reduced wave equation. Instead of minus Laplace potential, it satisfies this differential equation with variable coefficient. And then, as before, for any incoming wave, you can find a solution to this equation, and the outgoing wave such that wave is expanded like this. The sum of outgoing wave plus incoming wave. And the operator mapping A in to A out is the scattering matrix. So in this case, we are interested in the recovery of Gijx, G upper Ijx, and usually it is the inverse matrix of the Riemann matrix. So we are just led to the following problem: inverse problem scattering on Riemannian manifold. Namely, given Heisenberg's S matrix, can one determine the manifold? Now, what does it mean to determine the manifold? An example is a space. Manifold is simply a space. And I think the example of the manifold is our space. And in the classical idea, our space is flat and uniform. However, in the modern idea, it is no longer flat and no longer uniform. And it may have a form, or it may be curved And roughly, topology corresponds to the shape of the space. And whether or not the space is curved is related to the Riemann method. So what we want to determine is what we want to do is to determine the topology and the Riemann metric for the manifold. Now, what we have in mind is a manifold like this. It consists of a finite part, which can have any topology, which can have any shape, and infinite paths. These infinite paths are called ends. And this Riemannian manifold, M, is equipped with the Riemannian metric with G, G lower IJX. It's a Riemannian metric. It's a positive divine matrix, symmetric matrix. And the Laplacian on this manifold is defined by this second order differential operator. Here, G upper IJ is an inverse of this lower GIJ. Now, but manifold is a very huge object. So, what is natural class of manifold? We should study. So, given a non-compact, suppose we are given a non-compact Riemannian manifold with n dimension, and fix a point P0 arbitrarily. And let R be a point from P0 to P. Let R be a distant function of n. And a simple example of the metric is one program. It's written in this way. Assume that this non-compact n, this non-compact part n is isomorphic to 1 infinity times m, where m is a compact manifold of codimension 1. The 1 infinity and r, this r is 1 infinity. So suppose that, so consider this sort of m. And we assume that the metric is of this form. We consider metric of this form. Er squared plus some function rho r, and the metric on this manifold of codimension 1, m. And let G be the determinant of this matrix Gij. And natural assumption is that the logarithmic derivative of this determinant of this metric is bounded, where prime is the derivative with respect to r. In fact, if G prime over G is growing, then in general, the approximation of this whole manifold may not have continuous space. So we should study the metric which have having this property. And we further assume that G prime over G has a limit as R tends to infinity. C0 may be any real constant. It may be positive or negative or zero. It can take any value. Then, if you have this assumption, you can show that the continuous spectrum of the Laplacian on this end, this end, or this end, or this end, on any end, it has this property, the continuous spectrum of the Laplacian starts from this constant to infinity. So this seems to be a nice class to study the spectrum. Manifold And we pattern this method a little bit. We are considered we are considered in a case where this metric on M is independent of R. However, we consider a case where H depends also on R. But as R is infinity, is HMJX converges to HMJRX. This converges to this R. So this is the side conservation of this R independent method. There are also examples for this. If you take this row R to be e to the power R, this is the so-called standard hyperbolic method. You need to modify it. This is a big problem. If rho R is exponential, it's a hyperbolic method. If rho R is equal to R, it's a very standard Euclidean method. Euclidean, it just responds to case R. If rho R is equal to 1, it's a cylindrical N. So it's a 3. So this is the hyperbolic N. This is cylindrical N. If rho R is exponentially going to 0, the N shrinks to 1 point. And it also appears in mathematics. For example, in number theory, there appears manifold. Right? So to study this manifold, a nice function space is the space B star. What we want to consider is the solution of the Schrödinger equation. It's manifold minus the Laplace minus lambda. Lambda is we take lambda from the spectrum, and which behaves like a spherical wave. So it oscillates like this, and also with having this power. But you need to consider some weight. That weight should be this one. It comes from the standard volume element of the manifold. So the space E star is defined by is the set of functions U which has these properties. This is a convenient space to study the spectrum of this manifold. Now, the most important term to deal with the Schrödinger equation is the so-called Dirichlet. It's a kind of uniqueness theorem. And this sort of uniqueness theorem is always very hard in partial differential equation. In our case, it's like this. Let us consider the case of the Schrödinger operator on the Euclidean space. So consider the Schrödinger equation minus Laplace plus V, where V decays to 0 at infinity. And lambda is a constant. Then you can show that if you have a solution which maybe I have it may be. Maybe I made a mistake. If you decays faster than this power, E is always equal to 0. However, there is a solution which behaves like this as R tends to infinity, as we have seen. So this power is a borderline for the existence and non-existence of a solution to this equation. For the manifold, you have almost the same result. Let us consider 1N. This one or this one, this one or this one. Oh, if the doctor. This one, let us consider this. Now let us consider the one end, 0 infinity times f, equipped with a power curve work metric, where rho has this behavior at infinity. And assume that rho prime over rho is greater than or equal to beta over r, where beta is any positive constant. So this means that rho r details at least is polynomial order. Then you can show that if the metric has this property, and if you is a solution to this equation, and you have this property, then you can show that U vanishes near infinity of the manifold. So it means that whether or not U is non-zero or not is determined only by the behavior near the infinity of the manifold. This is a crucial step in our theory. Using this theorem, we can enter into the detailed properties of the shredding operator, and also proceed to the inverse scattering problem. Actually, this was the most difficult step of this one. We were working on this subject for almost 50 years. And almost 10 years ago, we used the structure of theory, but we could not prove this. We have very recently we have found the proof of this fact. Now, so the problem is not as follows. We consider connected non-compact Riemannian manifold consists of a finite part which has any equality and consisting of some parts which is growing infinity. And also, the other parts are shrinking to a point. We can also consider this cylindrical domain. But in this talk, we do not deal with it because it's a little bit different from the other. We can also deal with it. But today we consider only this one and this one. And each end has a part of product metric. And each metric on M we call M as a manifold at infinity. You have a metric where HMJ R corresponds. So converge HMJ as a alternative infinity. And when rho J goes to infinity, we call this n as a regular n. And when rho J R tends to 0, we call it cusp. So our manifold has cusp and also regular n. And so this is the hyperbolic n. This is another hyperbolic n. However, the slower the volume grows, the harder the analysis. So if the volume growth becomes slower, the analysis of the manifold becomes harder. Then what we are going to do is to introduce an analog of Heisenberg's S matrix. And from the S matrix, we determine the manifold. Now, this was the assumption. So we assume that each rho J converges to some point Cj, by which you can determine the spectrum of the Laplacian. And for the growing n, for the regular n, the logarithmic derivative of rho J is greater than or equal to some beta J over R. And assume that for the consequent, the rho j decays at least polynomial. This is our assumption. Then, letting Cj be defined by this formula, you can show that the spectrum starts from E minimum, where E minimum is an infimum of this constant for all n. Now, to study the Schrödinger equation with continuous spectrum, important role is played by the Fourier transform. How do you define the Fourier transform of manifold? First, let us consider the case of the standard Euclidean. Let us consider the Laplacian in 3 dimensions. Then the inverse of the Laplacian, the resolvent of the Laplacian has this integral kernel. This is the well-known formula for the integral kernel of Laplacian. Then, when R tends to infinity, it has this type of asymptotic function. When f is a nice function, say the rapidity function. And here you have a spherical wave factor. And here you have a Fourier transform, the function f. So it means that the Fourier transform of a function f is obtained from the asymptotic expansion as R tends to infinity of the Green's function of the Laplacian. So the spectral analysis of Laplacian, of the manifold, is done in the following way. Take lambda from the continuous spectrum of the Laplacian, and study the limit as epsilon tends to 0, where you take some spaces x and y, which sandwich the original space L to M. You take x space x slightly smaller than L2 and y greater than y with strong or weak topology, so that from x to y, this operator may have a limit. And you compute the asymptotic expansion as R tends near infinity of this Green's function. Then, from the first term, you will see the outgoing factor, outgoing spherical wave, or the incoming spherical wave. And as an amplitude, you can find the Fourier transform of the manifold. Here, x moves on the manifold at infinity. So in our case, it usually the S element. So from this plus and minus, you can get two Fourier transforms, f plus and f minus. They correspond to the outgoing and incoming waves. Those they correspond to outgoing or incoming waves. And by comparing f plus and f minus, you can get S wave. So this is the picture of the study of spectral theory of Laplacian manifold. So in our case, we take Y to be the space B star, which I defined before. So B star is defined as a function which has this quantity is finite for R greater than 1. And this we take phase function to be this one, where this rho is comes from this. And define H hat to be the space which becomes the target of the Fourier transform. Then, by looking at the Green's function, the behavior of the Green's function at infinity, you can define the Fourier transform on this manifold. Then, by this Fourier transform, you have the Fourier inversion form, which means that any function on this manifold can be developed by can be developed in this way, where this f plus minus lambda star is a sort of eigenfunction for this Schrödinger equation. So you have a complete analog of the standard Fourier transform. Now, how to define scattering waves and asymmetrics? We define this space for each end, and we consider the space of functions at infinity, which is the elliptic space over the manifold at infinity, and also for the cusp, it's merely the complex number. And Pj, the phase factor, is defined in this way. Then you can show that, just as in the case of the standard Laplace invariant space, for any incoming wave, you can find a solution to the Schrödinger equation in B star on this manifold, and also the outgoing wave into infinity, such that this U has this asymptotic exponential, where you have this phase factor, outgoing factor, plus incoming factor. And the mapping from A in to A out is the scattering. So it means that on each end, you have a scattering. So scattering operator is really a matrix of n plus n times n plus n times n plus n matrix. And each entry is an operator, and the diagonal component is the reflection coefficient for regular n or the cusp n. And our result is roughly as follows. Knowledge of the one reflection coefficient for the regular end or the cusp end is enough to reconstruct the whole manifold. This is our theorem. So, more precisely, the theorem says as follows. Let us consider two types, two sources in this manifold, M1 and M2. And let us pick up one regular endpoint, one regular end. They assume that each M1 and M12 is arithmetic. Arithmetic means that if you copy from here, there is some line, and this part and this part are arithmetic. If you cut it straight, this equivalent part is n, that's arithmetic. Then the associated 1-1 components, S1, 1-1, and S2, 1-1, coincide for all energy the complex spectrum. Then all manifold are asymmetric. It's 1 to 1, 1 to, and asymmetric. And so you must be careful that not only the metric, but also the topology to cover on this scale. And also to identify the manifold, only the knowledge from one data and that. And we are assuming that all manifolds are smooth, but we can also have a sort of similarity. The manifold is similarity appears in our state. So we can deal with also this sort of manifolds with points here. How to prove this so? It's rather long. And let us recall some classical ideas of inverse scattering, inverse spectral fast scattering problem. And the well-known approach to the one-dimensional inverse spectral problem is the so-called Gerber-Lipton multi-hex theory, proven in the 1950s. It deals with this one-dimensional Schrödinger equation on half-line or bounded interval 0, 1. However, there is an approach with the wave equation. The precursor of this wave equation approach was given by also in the early 1950s by M.K. Planck. And Dragovich-Chensky extended Train's idea to more, and the breakthrough to the multi-dimension was given by Berichev by this paper. He treats the case of the domain in the Euclidean space. However, Berichev and Friede extended his approach on Riemannian manifold, which is nowadays called the BC method, boundary control method. And very good exposition of this boundary control method is given in his expository paper appeared in Vast Program. It's a very, very good paper. Now, what is the basic idea of the boundary control method? So first we start with a compact manifold. Suppose you are given a compact manifold with boundary n. Then you consider Dirichlet problem. You consider Dirichlet Laplace on this manifold with boundary. Then there is an infinite number of eigenvalues and also the associated eigenvectors. And let us call the set pairs of eigenvalues and the normal derivatives of eigenfunction on the boundary. Let us call it the boundary spectral data, where this mu is a unit normal to the boundary. Then the theorem says that from the boundary spectral data, you can reconstruct the manifold. And so the compact manifold can be determined from the spectrum of the Laplacian and the normal derivative of eigenfunction in the boundary. Now, what is here? It's very interesting. Let us consider lambda, which is not a spectrum of the Laplacian, Dirichlet Laplacian, and consider the solution to this equation, Dirichlet problem. Then there is a unique solution to this Dirichlet problem. Let us consider the normal derivative of u as a boundary, and consider the operator from f to the normal derivative of u as a boundary. Let us call this Dirichlet to normal. Let us call it En. Then you can show that it's rather easy to show that the knowledge of this En map is equivalent to the boundary spectral data. So to know all the eigenvalues and the normal derivative of eigenvectors is equivalent to know the En map of all energy lambda. So to prove the theorem, you have only to show that given En map, you can reconstruct the manifold. And how to do it? To solve this problem, we consider the wave equation. we consider with Dirichlet problem. This is a bounded data with bounded data. We consider Dirichlet problem for this wave equation. Then the basic idea or the base of the BC method is to consider the mapping, which maps from the bounded data to the solution U. So it means that we consider a mapping from a function space on the boundary to a function space inside the manifold. Then, by using a solution to the wave equation, there's some uniqueness term for the wave equation. You can see that this function space, a function space on the boundary, contains a geodesic emanating from the boundary. And if you know the subject is geodesic, you can reconstruct the method. So from this function space, you can see the geodesic. And from this geodesics, you can reconstruct Riemannian method for the manifold. This is the idea of the field. And this idea for the boundary value problem for compact manifold are extended to the non-compact case by this paper. And how to use this boundary control method to the inverse scattering problem. The basic strategy is as follows. In our case, N is written as a union of compact part. The non-compact part is regular N, cusp N. We pick up one regular N. And suppose that the other parts are compact. Suppose that the other parts are compact. Then you observe this N and cut it here. And you consider this to be an exterior domain, and this to be an interior domain. Then for this interior domain, you can consider the electric form. Now you have a boundary here, and you can consider the EMF defined here. Then you can show that let S11 lambda is a matrix for this case. Then, if we assume that we know this part, suppose we assume we know this, then the knowledge of the S matrix for all S matrix is equivalent to this DNA. So suppose we know this part, then you can show that the knowledge of the S matrix is equivalent to the DNA for this particle. So from the scattering matrix, you can now you know the DNA. Then using this DNA, you can determine the manifold inside. Now, in our case, if you cut it here, this part is again a non-compact manifold. But however, you can do the similar, because if you cut it here, and using boundary control method, you can enter into the manifold activity, and you do the same thing. So you repeat this procedure again and again, and you can incorporate all manifold. This is idea of a proof. Now, so this is the proof for the regular N. And however, if the manifold is also cusp, the asymmetrics for the cusp does not have enough information to reconstruct the manifold. Usually, the insulating operator, the Laplacian of the cusp, has only the knowledge, one-dimensional knowledge for the spectrum. So the spectrum is simple for this cusp. So it is not enough to reconstruct the whole manifold. It goes to one point. So to deal with this cusp case, we enlarge the definition of the scattering. And using this generalized scattering matrix, you can show that this generalized scattering matrix determines the BM map for this interior domain. So in this way, you can reconstruct the whole manifold from this generalized matrix by using the boundary control method. And this sort of manifold we discussed also appears in number 7. In that case, this manifold has a sort of conic similarities. We sometimes call it ovifolds. But ovifold has also that it has similarities, but we can deal with a single manifold. So we can apply our theory also for this ovifold and reconstruct whole space. So what I want to say today is that if we want to determine the manifold, we go to the infinity and send a wave from here. And if you observe all the waves coming back to this end, you determine the whole manifold. This is the theory today. So thank you for your attention.
We have Professor Isozaki for the last talk. Any questions or comments?
Yes.
I think one important step in this in your theory is that you define the universe. You define the Fourier transform in this manifold.
Yes. Yes.
So we get the assumption that we assume U prime over U is bounded by C over R. Like, I think is this necessary for defining the Fourier transform? Or
Yes.
So this is a necessary step to define.
Yes.
Another question is that in the fusion, we define the topology and the metric of the manifold, and it seems that we only use the information of S11 or we only use the information of S11.
S11, yes.
But not the whole S.
It's a whole,
Yes. Is this because that this is a web product? So if this is, I mean,
yes.
So a natural, that's a guess. It seems if this metric is like dr square, dr square is dr1 square plus dr2 square, then plus some actual term in the isometric. Then
this is different. So yeah.
I mean, I just maybe so. Maybe then I think just from just a guess. So the results should related to S11 and S22. But
this is the so-called case of so-called rank 1 for symmetric space of rank 1. But you are mentioning the case of rank 2, higher rank. It's much difficult.
Oh, okay. So in general, just the flat metric.
Yeah.
Then it should related to all items in this S metric.
Yeah.
Okay.
So. So for the reconstruction procedure of the manifold, for the manifold, complex manifold case, we this but we do not use this property. This is what product. It was for every manifold in the paper of in the BC method. You can allow any method. You want to make it's one part.
Okay, but I feel a little bit strange because just for because if we don't consider the ends, just consider this bounded bounded domain thing. I feel strange. We can determine the metric for this domain just from S11. So it is still crucial for this something for the web product.
The S matrix, scattering matrix, is only the behavior at infinity.
Yeah.
Not here. We know only the behavior. The problem is whether we can determine something here. That's knowledge.
Yeah.
It's not so.
Okay.
So that's all the boundary. You don't do all the dictionary map here. Doesn't matter. The other hand.
Oh, okay. Maybe I need to read the paper to get more detail. Thanks.
All right. Any other questions?
Yes.
And does the framework work with the semi-linear matrix vector in velocity?
It's very good question. It's very hard. It's very hard. And firstly, is a self-bounding extension also is semi-linear. And also the uniqueness of the distribution also is for wave equation. There's no general theorem. That's the uniqueness of the wave equation of the data, only linear. It's a very good there.
All right.
Thank you.
Questions? Comments? Maybe I got a question. So basically, still we need to make use of all the energy, right? We need to make use of all the energy in this, all the energy, fixed energy.
The source of very
Okay, that's okay. So even if you assume this, for example, this manifold is simple, no method. Any other questions? No, let's thank Professor Isozaki again.